All right, so we'll work here with kind of a new lesson. This lesson is going to challenge your understanding of vectors so far. It is going to challenge your understanding of the way you think about our graphs. It's going to make you probably, hopefully, question and maybe connect a little bit more to numbers in the world around us. We'll see. It's going to be a bit of an adventure. At times your head might hurt, and that's okay, that's a part of it. If so, take a step back, wander around, take a break, come back, and play around with it. So, our work so far in this course, in advanced functions before this, in grade 11, 10, and 9, and into grade 8, I think, is when you started to work with graphs. That's when you started to work on what we call the XY plane. You may have heard me refer to this as a Cartesian plane. Your Cartesian plane has an X and Y axis. It has two axes. Your vertical axis is Y, your horizontal axis is X. Now, each point on this Cartesian plane, on this two-dimensional Cartesian plane, every point here is unique. And that means, let's say I choose a point around here. I don't know, this could be the point 4, -3. And this point 4, -3 is described by this ordered pair 4, -3. And if I choose any other numbers, then my point might end up in a different location. But if I'm choosing different numbers, my point will not end up in this same location because this point is unique. Okay, well, that also works in the other direction. So if I start off with coordinates, I don't know, say 4, -3, there is only one location on this entire map, on this entire Cartesian plane. There's only one location where this point might fall, and that's right here. All right. Now, that's all well and great, but the points are not contained to 4, -3. There are an infinite number of points because there are an infinite number of x coordinates we could use, and there are an infinite number of y coordinates we could use. Now, we can connect this to our vectors a little bit further, so we could actually create a vector in here. We could create a vector using this point 4, -3 by putting the tail of a vector at the origin and heading out to that point. Now, we could always do this. We could consistently create vectors and define vectors in this way, where I could call this vector v is equal to 4, -3. We could define vectors like this consistently so that we can follow along and work with them, label them, define them to accomplish our goals. Now, okay, what if we consider all of these possible points for point P? And we can call this point P. Up here it's 4, -3, but really it can have any x value, any y value. Well, if it can have any x value and any y value, then we say we're working with x is an element of the reals, and we're working with y is an element of the reals. Now, the collection of all of these possible points is given by what we call R2. We say we're working in R2 if we're working in the space defined by all of these x values and all of these y values, which is the space in which you have been working year after year after year after year. This is our workspace. This is our canvas. This is where we can paint, we can play, we can work with vectors, we can work with functions, and you've been doing that for a very long time. But what if we want to get more ambitious? What if we want to play around a little bit further? What if we recognize, okay, well, this workspace right here, this has done the trick for a little while now. It has allowed us to work with functions. It's allowed us to describe some variables in the world around us, but we're drawing this space on a two-dimensional flat object, whether it's your piece of paper, whether it's my computer screen. We're drawing this in 2 dimensions. We're only describing 2 dimensions. And the problem is we're using these 2 dimensions to describe this 3-dimensional world in which we live. So we'll play around. We're going to jump a little bit further. Because if you are in your, I don't know, in your kitchen, in your bedroom, in your living room right now, if you're at a desk, at a table, you can reach out and you can touch things. And you can reach straight out ahead of you. That's forward and backward. You could reach to your left or to your right, or you could reach up and down. And we could describe all of the directions that our minds are ready to understand. We could describe these directions with 3 dimensions: left, right, up, down, forward, backward. Or if we look at our directions on a compass rose, then we're looking at north, south, east, and west, and up and down from the surface of our planet. So we're describing these with 3 dimensions. And if we're going to assign 3 dimensions in math, we're going to work in 3 space. All right, so we've already worked with x dimensions and y dimensions, x coordinates and y coordinates. Now we're going to play with a new coordinate, the z coordinate. So bear with me right here. This might be a little bit uncomfortable, and that's okay. So we'll work here and we'll start, and we're only going to sketch our positive axes right now, and then we'll sketch in our negative axes in a little bit. So this first axis, it goes up and down on our page. We're actually, when we're working in 3 space, and this might be a little bit uncomfortable at first, and that's okay. You're used to this being your positive y-axis, but in 3 space, we're going to call this our z-axis. All right, now if we go 90 degrees to the right, we're going to work with what we call our positive y-axis. Let's give that another color, our positive y-axis right here. All right, and then even further, we need to be able to demonstrate, we need to be able to show on our piece of paper, we need to be able to show what we're doing. We need it to look like 3 dimensions. Well, what's something 3-dimensional that your minds are used to looking at all the time? Corners. So we'll take advantage of that, and we'll call this our x-axis. Now, this is what we call a right-handed coordinate system, where if we pretend we're looking down from the z-axis, then 90 degrees clockwise from y, we would find our x-axis. This is what we call a right-handed coordinate system. This is going to be the convention that we use in this course. It's going to be the convention that you use in your future courses. And by following this convention consistently from course to course, from chapter to chapter, from conversation to conversation, we're all able to work together in a way that falls together nicely, that avoids unnecessary confusion. So if you're uncomfortable with this, that's okay. You will be uncomfortable with this right now. I would expect that, and I would expect that probably for at least a few days of working with this until we can play around a little bit more. Now, we're working here with 3 different coordinates, x, y, and z, where any of these coordinates, x, y, and z, can take on any value from the real numbers. They can take on any rational value, any irrational value, any positive or negative value. So we're working here and we say, okay, well, we're working from the reals in x, we're working from the reals in y, and we're working from the reals in z. So we multiply all of these together almost, and we're working with r cubed, but we pronounce it r3. So we're working in r3, and this is in 3 space. All right, so the origin in r3 can be given by the point 0, 0, 0, where we always list our points in 3 space alphabetically: x, y, z, just like we listed them alphabetically when we worked in 2 space for the last 4 years of math. So any point x, y, z can also represent a vector from the origin to that point x, y, z. So if I'm trying to find a point, let's see here, let's zoom in, we'll play around a little bit. If I'm trying to find a point, and this might seem a little bit, honestly, this entire lesson might seem a little bit overwhelming at times, that's okay, we'll play around, we'll get there. If I have a point if I have a point, and my point is given by x, y, z. For example, in this case, I'm going to use the point 1, 2, 3. All right, so my x coordinate is 1, my y coordinate is 2, my z coordinate is 3. We'll play around with it here. So this point, and I'm trying to select it, there we go. This point, we consider it at our origin at first, and then we can follow along. Okay, so let's go in the x direction 1 unit. So that might be, bear with me here, that might be along my x-axis that far. There we go. Oops. I'm struggling. That's okay. We'll get there. Along our x-axis, 1 unit. We'll label that with a 1. Okay, and then I need to go along my y-axis 2 units. My y-axis, that's this one here. My positive y-axis, so I'm going to the right 2 units. I'm probably looking at something like this, where you might notice, okay, so it would be like 1 unit and 2 units. So it almost comes out in a parallel direction to my x-axis over here. So my parallel direction, it's like I'm coming along from here. There we go. We notice we're moving along. And then I need to work with my z direction. So now I've gone with my x coordinate of 1. I've gone with my y coordinate of 2. Now I need to work with my z coordinate of 3. Z here is up or down. So if I'm going up 3, up is positive z, then I'm going up 3 units, something like this. And I'm just obviously guessing here, but say 1, 2, and 3, where we're playing around, and we could visualize, I'm hoping you can follow along here, we could visualize still our x coordinate came parallel, we'll draw this parallel, there we go, 1 unit. Our y coordinate was to the right 2 units. And our z coordinate has gone up here by 3 units. So I'm hoping you're able to follow the sketch that we've made here. It almost makes a rectangular prism if we connect everything in place here. There we go. We're visualizing it. We're able to see what's going on, I hope. And if not, that's okay. A little bit more practice will get us there. So, excuse me. In R3, we have 3 axes. These axes are the x-axis, the y-axis, and the z-axis. Now, if I am to take a look at these axes, all I have sketched on my page and all you will sketch on your pages are the positive axes. But if I'm looking, let's say, at the negative z-axis, then that would continue down here. If I'm looking at the negative y-axis, that would head to the left of my z-axis, way over here. Good. And if I'm looking at the negative x-axis, it would go back into the page like that. So we can view our 3-dimensional Cartesian plane here, our right-handed coordinate system. We can view this as y and z lie flat on the page. Positive x comes out of the page towards you. That's how we're going to be describing it here. All right. Now, we're going to look at this diagram. Good job, us. It's right from our textbook. And we're going to try and find the points, the coordinates of the point C. So we'll look here. Okay, so we have the point C. And we know our coordinates are always listed x, y, z. Now, our x coordinate is always given by my positioning along the x-axis, just like when you worked in R2 for the last 4 years. So my positioning along the x-axis, okay, so I see the origin right here. I see the point P lies at what we call A, B, C, where A is the x-coordinate, B is the y-coordinate, and C is the z-coordinate. You'll notice these are general coordinates here. They're given by variables, and that's okay. So if I'm trying to find point C, which is given by a capital C, and I wish they didn't overlap like this, but they do. If I'm trying to find point C, then I can do so by asking, okay, what is the x-coordinate? Along my x-axis, how far do I go? Well, I notice here that it shares the same x-coordinate as point P. It shares the same x-coordinate as point P. So I'm working here, and my point C, all right, well, I'll be working with C is given by the same x-coordinate, so that is A. And then I look and I say, okay, what about my y-coordinate? Well, my y-coordinate is my distance to the right of what we call the xz plane right here. All right, so to the right of the xz plane, well, hang on. Point C is right on that plane. Point C is to the left of point P. Point C does not share a B coordinate. Point C has a y coordinate of 0. And then we need to find the z coordinate. Okay, so how far up from the origin have we gone for point C? Well, we've gone up the same distance as point D, right? We're going up that same distance, and that's the same distance from point B to P, and that is the distance given by this C here. So our coordinates for point C could be given here by A, 0, and C. Then let's look at point D. Okay, point D, I'm looking way over here. Now, point D has only traveled in one dimension from my origin, right? It's just one straight line away from my origin. So if that's the case, only one coordinate will have changed. It's up to us to determine what coordinate has changed from the origin, right? The origin was 0, 0, 0. And now one coordinate has changed. In which direction have we gone? We've gone up. Up means we're looking in the in the Z direction. So if we're looking in the Z direction here, we've gone up, then we need to work with our Z coordinate. We're going to work with a C. So our point D can be given by the coordinates 0, 0, and I'm lagging a little bit here. There we go. Trying it out. There we are. 0, 0, C. Fantastic. So I'll ask you folks, try it out on your own. Try to find the coordinates of point E. Try to find the coordinates of point F. Those will be included in the uploaded note that I put on the classroom. We'll push forward, though, into example 2. So here we have another diagram. All right, so here we have a rectangular prism. And point P, you know what, did we follow on the instructions? Yes, we did. Okay, so point P is at 6, 2, 4. And again, we want to try and find the coordinates of all of the points here. Well, together, we'll find some of the coordinates, then we'll play around with it a little bit and leave you to finish it up on your own. So let's start off. Okay, so we have the origin. Now, if I look at this, I can look at this kind of in a simple fashion. I can break it down, and I can say, okay, point A has only been moved, if you will, by one coordinate from the origin. Same with point F. Same with point D. How do I know that? Because those points lie right on my axes. So, if that's the case, we'll work with point A first. Point A moves in only one direction. It moves in only one direction. It moves in the x direction. How do I know that? Because it's along my x-axis. So if it moves in my x direction, point P is has the x coordinate 6, then point A will be found at 6, 0, 0. Good job, us. All right, then let's look a little bit further. Point D, we said as well, only differs from our origin by one coordinate. So point D works in the Z direction. How much has this gone up? Well, it's gone up the same number of units that point P has gone up, and that is 4 units. So point D, I'm working with 0, 0, 4. Nice work, folks. Okay. Point F, I said was the third option there. Point F has only been transformed by 1 unit. So by one particular coordinate. So if I'm looking here, I need to break it down. And which coordinate is it? Well, it's moved to the right. To the right means I'm working in the y direction. And if I'm working in the y direction, that means I must share the same y coordinate as point P. And I can see the consistency here. Yes, that's true. I'm working with 0, 2, 0. Good job, us. Now, you might notice a little bit of a pattern in here. If that's how I found points A, D, and F, I can find next points B, C, and E through traveling in 2 directions. It's almost like how we have traveled with some vector addition, how we've made that a journey in the past. So let's look at point B first. For point B, well, I travel from the origin. How do I travel from the origin? To point A. and then I travel to the right to point B. So it's like I add the vectors, right, from the origin to point A plus the origin to point F. So I'm working here. Point B will share the coordinates. Point B will share the coordinates with A, so it'll share that same x coordinate, that's 6. And it's going to share the same y coordinate as point F. So I'm working with 6, 2, still 0. Fantastic. Now you folks should be able to handle point C and point E, and then go through the logic for how we could consider, with some vector addition, how we could find point P. Try it out on your own to finish this. Again, the solutions will be posted on the classroom. We're going to push forward in the video, though, to example 3. We have, in total, there are just the 4 examples here. So this third example might be a little bit more challenging to visualize. So let's delve into it a little bit here. The key is to try and find, if we're trying to visualize here what's going on, is to try and find along which axis one of the edges of our shape lies. So we can see here, and it might be difficult to make out on your screen, but we can see between points origin and point P, our edge of our rectangular prism follows right along our y-axis. And that's the whole key. So this question asks us first to determine the coordinates of all the points. Then we're going to sketch a vector when we're finished with that. So let's play around. Okay, again, following the same logic that we've been practicing with our vector addition. Let's look at point P. Well, point P only travels in one direction from the origin. Which direction is that? It travels to the right. So if it travels to the right, then point P will share the same x coordinate and will share the same z coordinate as the origin. It has only moved in the y direction. How much in the y direction? That is given by point T down here. It's traveled 2 units to the right. There we are. P is at 0, 2, 0. Okay, now we could play around a little bit more, and we could say, hang on, R also lies on one of our axes. Might not be immediately obvious, because R lies on the negative z-axis. So it's only translated, it's only being moved along one coordinate from the origin. Okay, well, if that's the case, you folks should be able to come up with your coordinates for R, and using that same logic, your coordinates for M. So try that out. Pause the video, try it out, and then you can unpause to compare your work. Nice job, folks. We have R at 0, 0, -2. We have M at -3, 0, 0. Okay, then using that same logic that we used in the past, let's work forward, and we can find Q, we can find N, and we can find S through using that journey of vector addition. So it's like we travel, okay, down to point R, if we're going to point Q. And then we travel across to point Q. So point Q will have 2 dimensions changed from our origin. Which dimensions are those? Well, the first dimension that gets changed is our Z dimension, because we're going down. So if we're going down here, we're going down 2 units according to this point T. And then I'm also going to the right to point Q. So if I'm going to the right, well, that's the y direction. So that means my y coordinate changes to 2, and my x coordinate remains 0. All right, so you should be able to follow this same logic. Try it out, pause the video, compare your work. Here we are. We have S at -3, 2, 0. We have N at -3, 0, -2. Well done, folks. Now, lastly, this question is asking us to sketch the vector OT, and that's from the origin to point T. Now, this is much easier, perhaps, than it sounds. Maybe it doesn't sound that challenging at all. All we're doing, we're going from the origin to point T. There we go. That is vector OT sketched in place. Well done, folks. Now, OT, we know here, OT can be given by the coordinates of the point T. So OT is equal to -3 to -2. Well done, folks. So it points in the direction from the origin to point T, and its magnitude, we're not sure of the magnitude, but we do know we can demonstrate it. We can represent it with this ordered, what we call an ordered triple. All right. So you folks have worked, believe it or not, in R2 for so many years, but before that you worked in R1, and we've actually worked in R1 a tiny bit in this course. R1 would have just one dimension. So R1 would look something like this. What does this look like? You guessed it, a number line. Okay, now in R1, if I have, say, I don't know, x equals 3, then what I have is a point, right? My point at x equals 3. Okay, that's great. Now when I work in R2, we've been working in that for years. It's a Cartesian plane with x and y coordinates. In R2, if x equals 3, then that's not a dot, is it? That's not a point. That is, in fact, a line. X equals 3. Okay, in R3, if we're working with x equals 3, then that includes all of the points that exist where x equals 3, just like in R2. This is a collection of all of the little points that exist where x is equal to 3. In R3, I want you to try and visualize what will that shape look like you're about to see. So we'll work here. We're working with example 4. All right, example 4, and I'm wondering if you may have guessed it by now, folks. We're going to work with planes. Now, planes at times, just like, frankly, a lot of the work in R3, planes at times can make your head hurt. That's okay. It's new. That's normal. The expectation is this is a challenging course. The material is going to be challenging. So we want to look in here. We want to visualize the XY plane. Now, we've been able to visualize the XY plane for years in R2 because all it looks like is this. But we're not in R2 anymore. We're no longer in Kansas per se. We're working in R3. So if we're working with the XY plane, then that plane, if we visualize it on here, okay, so we see R3, we can ignore this rectangular prism. I apologize for that for now. If we're coming up with the XY plane, then we're coming up with all of the points that are shared along this flat surface. This flat surface in here. We're working along the XY plane. Now, there is one coordinate that points in all of these locations share. There's one coordinate shared along this plane, and that is the z coordinate. So if we're looking right on this plane, then our x coordinate could be anything and it could fall on this plane. Our y coordinate could be anything and it could fall on this plane. But as soon as our z coordinate changes, then we go above the plane here. That might seem a little bit tough to visualize. That's okay. We'll get there with practice. So if that's the case, if all of these share the same z coordinate, z equals 0, then our plane can be defined by this equation right here, z equals 0. It's that simple. It's that straightforward. So you've seen before, if we head back to our first discussion here, a number line, x equals 3, is a point. If we're working in R2, x equals 3 is a line. If we're working in R3, x equals 3 will become a plane. All right. Now, we want to look at points P, M, Q, and T. And I'll erase some of this work with my black lines. There we go. If you're curious how I came up with those lines, if we're working on the X, Y plane, then I'm drawing those lines in between my X and Y axes. All right, so that should allow you to visualize a little bit the surface on which we're working there. Fantastic. Okay, so we're looking at the points P, M, Q, and T. I have the point P here, I have the point M, I have Q, and I have T. Now, we need to track our directions, particularly for points M and T, because it's not immediately obvious where those fall. But if we follow the same logic we used to come up with our z equals 0 plane with our xy plane, we should be able to come up with a plane here to describe these points. So these 3 points, P, M, and T. Whoops, I have a Q in there as well, shouldn't I? There it is. P, M, Q, and T. If they all fall on the same plane, then they should share one coordinate fully, because that same logic I used up here, all of those points share the coordinate. Which coordinate? Z equals 0. So down here with P, M, Q, and T, let's look. Okay, our x coordinate for P and M is 0, 2, 0, and 2. So no, that coordinate is not consistent. My y coordinate is -3, -3, -3, -3. There, I found it consistently. All of these points will fall on the plane y equals 3. Fantastic. All right, now let's look at that rectangle, P, M, Q, and T. And we want to describe all of the points that fall inside that rectangle. How many points fall inside that rectangle? An infinite number, even if the space, the surface area involved there is not infinite. Okay, so we're looking on this plane. We're looking in this rectangle, and we're describing all the points. Well, all the points we just checked, all of the points have the same y coordinate. Y equals 3. Whoops, y equals -3. Sorry, folks. We're trying to correct it. It's lagging a little bit. That's okay. There we go. Y equals -3. I'll just squeeze that in. Fantastic. Then we look at our x coordinates. Okay, well, my x coordinates that I see in here on my points, which are all on the edges of this rectangle, my points, okay, so my x coordinates, I'm working with 0 and 2. Those are my only options. Now, are those the only options for all of the points falling in this rectangle? No, because my points can fall with my x coordinates. My points could fall with any value in between 0 and 2. So here I would say, okay, x is an element of the reals such that 0 is less than or equal to x, which is less than or equal to 2. Okay, so y has to be equal to 3, but x can fall anywhere in between 0 and 2. Then let's look at my z coordinates. Well, I'll be using the real numbers as well to describe my z coordinates. My z coordinates, let's see, I have 0, 0, okay, -5, and -5. And if I take a look, all right, my z coordinates, they can fall anywhere between this 0, right here, and my -5. They go down in this direction, down to -5. So I'm working here, and I need to make sure I list the lower number first. So -5 is less than or equal to z, which is less than or equal to 0. There we have it. We've described the points that are all on this y equals 3 plane, but not all of the points on that plane are we describing here. We are just describing the points inside this particular arbitrary rectangle. And lastly, we're going to look at the plane, the plane parallel to the xy plane, but passing through point R. Where's point R? Here it is, down here. So if it's parallel to the xy plane, we want to visualize this plane getting picked up and moved parallelly along to here. Okay, so if I'm trying to describe this plane right here, I need to find the coordinate that is consistent. Okay, if I'm looking right here, well, does my z coordinate change? Yes, it can go up or down. Does my x coordinate change? Yes, it can go out of the page or into the page. Does my y coordinate change? No, it does not. My y coordinates never deviate left to right here. So I'm working, and this plane can be given by y is equal to 0 because they all share that same y coordinate. So with a little bit of practice, folks, we will be able to handle all of the practice problems here. Well done. We'll get more comfortable working in R3, working in 3 space, and working with planes.